Exercise 1516 gives you the reactants or reagents for a reaction and asks you to distinguish between the reactant and the product using IR spectroscopy. So the reagents they give you first are 1-butene and sodium amide. So first let's draw those. We'll see how they react with each other. We'll use the principles of drawing mechanisms with nucleophiles attacking electrophiles to figure out the products, and then we'll compare the reactants with the products using the shadows they would each cast in IR spectroscopy. So 1-butene. Now the infix here, YN, is telling you that you're dealing with an alkyne. So that's a carbon chain that has a triple bond. So whenever you have an alkyne, always draw that triple bond first, because the carbons that have a triple bond are linear, and so they're a little weird to draw. It's not just your usual zigzag. So here, it's 1-butene, so that means that the triple bond starts on carbon 1, and it always goes to the next number, so this is carbon 2. Now we need a total of 4 carbons. That's what the prefix but is saying. So we have 1, 2, 3, and notice I put it in a straight line because carbons involved in triple bonds are linear. 3, and now it can start to zigzag, and there we have 4. So here it is, 1-butene. Okay, next, they give us sodium amide. Now sodium amide, sodium is Na, and amide is NH2. And you might notice already, sodium, that's a metal. Metals have very low electronegativity, so anything that they're bonded to is going to steal the electrons from them and actually have a negative charge, and the metal will be positive. Let me put that in colored. Okay. So the sodium is going to go off. It's just there to help to stabilize the amide so that it doesn't explode when it's in a jar on a shelf in storage. Once you put it into the beaker, it floats around and goes off and does its own thing. It is the amide that's going to react with the alkyne. Now if you remember, any carbon in a triple bond is sp hybridized. Remember that you have each carbon has in its valence shell, it has 1 s orbital and 3 p orbitals. One in the y direction, so py, one in the x direction, so px, and one in the z direction, so pz. And it can use those p orbitals to create pi bonds. A pi bond is a bond that has an interruption in the overlap of the orbitals. So if you compare a sigma bond, you'll have 2 orbitals that overlap. For example, here they're s orbitals, and the overlap there, let me just do that in a different color, this overlap in orange is not interrupted, it's continuous the whole way. When that happens, you have a sigma bond. Compare that with what happens when 2 p orbitals are parallel and overlap with each other. So you have 1 p orbital, and then you have another p orbital. And you can see that they do overlap. They overlap in these 2 orange places. And that's what creates the bond. But in between, they do not overlap. And that interruption there is what makes it a pi bond. A pi bond is overlap that is interrupted once. It also means that pi bonds are weaker bonds than sigma bonds. Now, let me actually use a different color for this overlap. I'll use purple. The first bond you ever form is a sigma bond, so this first bond here is a sigma bond. Every bond after the first bond is a pi bond, so this is a pi bond, and this is a pi bond. If you have 2 pi bonds, like we do here, then that means you need 2 p orbitals. 1 p orbital for each, on each atom, for each pi bond. So this carbon here, this sp2 carbon, has 2 pi bonds, so it needs to have 2 p orbitals. That means it can only combine an s and a p orbital left. That's why it's sp hybridized. But notice what happens when you mix different types of these orbitals. You could mix the s orbital with all 3 p orbitals, and that would give you a new Frankenstein orbital sp3. That's 75% p. 3 p's, 3 parts p, 1 part s, 75% p. And so it's going to really look like a p orbital. It's going to be long like a p orbital. With an sp2 orbital, you're mixing 2 p's, 2 of the p's, with the 1 s. So now this is only 2/3 p. And so it starts to resemble an s a little bit more, becomes a little more spherical. With an sp orbital, like what we're dealing with in this molecule, it's 50% s. Now you've only mixed 1 of the p's with the s, so it's 50% s, and it really almost looks like a sphere. Okay, so how does this all fit in to how these two molecules are going to react? In an sp hybridized carbon, if you think about which of these orbitals, sp3, sp2, or sp, which could handle a negative charge the best, it is the sp hybridized orbital that could, because here's where the nucleus is. The nucleus has positive charge, and it's hugging that negative charge. It's hugging these electrons really close to that nucleus, whereas with sp2 or sp, the electrons venture further away from the nucleus. And it's because sp orbitals can stabilize the negative charge, a negative charge on them like that, that hydrogens that are bonded to a carbon with an sp orbital are able to pop off. Because if these electrons just go back onto the carbon can handle that negative charge because the orbital hugs the electrons really close to the positive nucleus. All right. So even though this hydrogen does not have a positive charge on it, it is vulnerable. It is able to leave. This amide, which has a full negative charge, is able to steal it because the electrons can go back on that carbon and be stabilized by being close to the nucleus. So that's the first step in our reaction. And what happens after that step is you have your triple bond, the other carbons didn't change, but now this bond here becomes a lone pair, and carbon gets a -1 formal charge. And now you have NH3. Now, we're actually able to appreciate why this ended up acting as a base and stealing a hydrogen. In general chemistry 2, you would have been in 1 even, you would have been introduced to NH3 ammonia as a base. It's a weak Bronsted-Lowry base. Amide, NH2, with a negative charge, is the conjugate base of a base. It's a really strong base, and so it tends to steal hydrogens. Okay, I'm going to actually just move this ammonia. It floats around the molecule. Maybe it has a conversation with the sodium in the corner. It's not relevant to us anymore. So that's the first step. And then they say it's followed, in this question, it's followed by ethyl iodide. That means we're dealing with 2 carbons. So here's 1, 2, so 2 carbons. And coming off of those, and it doesn't matter where because the molecule is symmetrical, you have an iodine. So that's ethyl iodide. All right, well, iodine is all the way on the right on the periodic table, so it's kind of electronegative. Steals some electrons for itself, becomes slightly negative, and the thing it's bonded to is slightly positive. And let me just draw this negative charge in red here so it's easier to follow. And so the alkyne, this carbon nucleophile, is going to attack the slightly positive carbon. So it attacks this, and if that new carbon can only have 4 bonds, if it's going to make a new bond, it has to break one of the ones it has, and so it breaks the bond to the iodine. First, because it's the most electronegative place nearby, and so the electrons would prefer to go there. And also the bond is weakened, there's already a separation of charge, And also, iodine is enormous. Iodine is like a gigantic monster. And so it's a really good leaving group because if it has to have a negative charge, it can spread it out over a gigantic area so that at any given area there isn't as much charge, and so it's more stable. So the iodine kicks off. This right here is an SN2 reaction because you have the nucleophile coming in and the leaving group leaving at the same time, two things happening at the same time, resulting in the substitution of one with the other, of one molecule with another. So SN2, substitution. And let me write numbers for this just so it's easier to see. It's so easy for carbons to just magically drop out of molecules. So there we have our 4 carbons, and here I'm just going to put 2. Okay, so let's draw first the alkyne. So there's our triple bond, and then that's our 4, right? So just so we can follow, 1, 2, 3, 4. And we're going to add 2 carbons to that. Now keep in mind, triple bonds have to be linear. So this is going to come linear. It's not going to zigzag. That's going to be our first. That's 1 carbon. But we need 2, right? We need 2. So this will be our second. And the iodine, of course, is off somewhere, probably making friends with the sodium and the ammonia, another place in the beaker. So this is our product. Oh, so is that the end of the exercise? It is not. Remember, the whole point here was to talk about how you could tell whether this reaction happened using IR spectroscopy. So let me erase this other stuff. Let's just zoom in, hone in on our reactant and our product. So here I'm going to put our reactant in orange and our product in blue. Oops. So how would these differ in IR spectroscopy? Well, one thing, this has an sp hybridized carbon with a bond to a hydrogen, and that has a signal at 3300 wave numbers. If you look back at that table that we used in the last few problems, that's one of the 9 shadows that you want to remember. And if you compare that with the other molecule, this one, the product, does not have that. Now you still have the sp hybridized carbons, but it's neither of these carbons are bonded to hydrogens, and it's the hydrogen bond that absorbs at that wave number. And so you can distinguish between these two by seeing whether you have this shadow or not. If there is a shadow at 3300 wave numbers, then you have the reactants. The reaction didn't happen. And if it doesn't, then all the reactants must not be present. They must have turned into products. The specific wave, so I'm only going to give you the wave numbers on a test that are in that table, those 9. But the wave number that's given in this particular problem is 2200, you might notice. They say that it appears in this IR spectrum of the starting alkane, but that shadow does not appear, it's not observed in the IR spectrum of the product. Why? Now, we were talking about 3300. 2200 is a shadow that you're not responsible for the test. It's the absorption between 2 carbons that are triple bonded. Now you might say, wait a second. The triple bonded carbon is here, so it makes sense that it would be observed in the starting alkyne, but it's also in the product, so why is it not observed in the IR spectrum of the product? And the answer to that is that this molecule is perfectly symmetrical. Perfectly symmetrical. And remember that light only interacts with charges. Light is a wave of electricity, and so it will only interact with electric charges on molecules because this molecule is perfectly symmetrical. There is no separation of charge. There is no dipole here. And so light will just move right through it. Light will get absorbed by this one, but it'll just move right through this. Because the first one, the 2 sides of this bond are different. Here you have a hydrogen with a certain electronegativity, here you have a carbon with another, and so however tiny, there's a certain charge on the two sides of this. This would happen to be tiny, tiny small charge, tiny, tiny positive charge. And it's that light interacts with, whereas because this molecule is perfectly symmetrical, there is absolutely no difference in charge anywhere in this molecule, and so light, or at least not involved with a triple bond, and so light wouldn't interact with that. So this is a sort of combination problem using curved arrows to show a mechanism and predict a product. And so this is one of the reactions you should know for this test from Organic 1, namely sodium amide with a terminal alkyne, an alkyne at the end of a chain that has a hydrogen, and also using that carbon nucleophile with an alkyl halide, giving you a substitution product. And we're combining that with IR spectroscopy so that you can verify whether you got that product or not.